Hi, everyone. Thank you for joining us today. We're just going to give it a moment before we start, let everyone log into the Zoom. Just want to make sure no one misses anything. So we'll just give it one moment. Great. It looks like we've got a good amount of people logged in now. So let's get started. Hi, everyone. My name is Courtney Brown, and I'm a Senior Marketing Manager here at EDB. I'll be your host today for our webinar, Power JSON with PostgreSQL, and this is Volume 2. We had a Volume 1 back in January. Don't worry if you did miss it. We'll be sending out a link to the recording of that one as well, so you can reference it. I'm joined today by Simon Riggs, Postgres Fellow here at EDB. And before I turn it over, I'm just going to go through a few housekeeping items. This presentation's being recorded. We'll be sharing the recording along with the slides after the broadcast to the email address you used to register for the webinar. All of your lines are currently muted. If you do have a question, please feel free to submit it into the question panel. We expect the presentation will last most of our time today, but any extra time we'll use for that Q&A. If we don't have time to address all of your questions, don't worry. We'll follow up afterwards with personal answers. And now I'm going to hand it over to Simon to kick us off.
Thank you very much. Okay, so Power JSON. Why are we talking about it? Well, JSON is a very important data type in the modern world, and it's normally something that we just speak about as a kind of throwaway line. Yeah, we do JSON, as if as if it was an afterthought. What I intend to do in this presentation and the previous one as well is to show that not only do we support JSON and store it, but we do that very well. And we've got lots and lots of support functions that are genuinely useful in your application development work, and obviously in the databases that that match with that. So this is part 2, and obviously if you missed part 1, please go and have a look at the recording for that before you look at this one. So if you didn't attend the earlier one, then I hope that you're able to follow what goes on here. This is going to be more advanced, different topics than we talked about before. So it's not a basic introduction to JSON, and you may well be confused. Okay, so there are potentially many questions that you might ask around that confusion, and unfortunately I will avoid answering those basic types of questions because the answers are addressed in the earlier part of this webinar. So we're going to talk about SQL JSON and schema design. Those are the 2 topics that we've got today. So not talking about basic JSON at all. So all of the examples that I'm going to use are based around a very simple piece of JSON. So like one piece of JSON in a table. Obviously, Postgres can store many millions or billions of records containing lots of different JSON objects, but obviously we wouldn't be able to fit those on the screen. Okay, so my examples refer logically to this piece of JSON. So as we're going through, you'll see that it's got numeric, it's got integer, it's got timestamp, it's got text, it's got Boolean, it's got arrays, it's got nulls, and it's got embedded JSON objects within it as well. So it's a good example of the types of JSON that exist in the real world, even if it is clearly not a piece of real JSON. Okay, so my criteria for picking this is it shows the types of complexity that we're using and it fits on the screen, which is always a good criteria for any presentation. Okay, so what I'm going to do with that piece of JSON is I'm going to show you how to do advanced search using the SQL JSON language, also known as JSON path. Now, this is something that is now fully within PostgreSQL, so you don't need to install anything in order to get all of these to work. But the documentation, as ever, is precise, but it doesn't introduce you to a lot of the concepts that we might want to look at. So just to reference the example is that I've got a table called J, and within that table there is a column called JDoc, and JDoc has been defined to be a data type of JSONB, which is the binary data type that PostgreSQL uses to store JSON data. So an example of a query from that table would be select JDoc from J, where JDoc at, and then we've got this phrase exists bracket $.new that is the search query. So the at or the at question mark references a constant, which is a search term. So this the exists is encapsulated within two single quotes to show you that that's the edge of the language that we're using. So it's an expansible language. We can write quite complex searches in it. But what I want to do is introduce you to some simple searches so that you can begin to understand how this is working. Okay. So just to explain that a little bit more. So JDoc is a column within a PostgreSQL table, and at is an operator. So what we're actually asking PostgreSQL to do is we're saying take this string called exists something or other and use that as an operator on the JDoc column. Okay, and at means take the string, use it to search within that column. Okay, obviously if I used a different operator like concatenate operator, which is 2 bars, then we'd have something completely different behavior. So obviously this is relevant to this specific operator that we're using. Now obviously what you can see is that exists search will actually check whether there is a field called new at the top level in the JSON document. So $ references the root of the JSON document. Okay, and then if you put dot something after the $, you're referencing a field name that is one down from the top. So if we look back at our example there, you can see that the top level JSON contains a field called OID. So if we were to look for $.OID, we should find that within our JSON. Okay, so what this is asking is, does a field called new exist one level down from the top of the tree of JSON within that document? Now, obviously, within the example JSON we have, this will not find anything because of the existing field names within my example. Now, just as a side note, the exists form is not indexable, so it's not that useful. So a much better way of looking at this would be to actually look for the value itself. For example, if we want to search the field new to see if it has a value of true, we can say $.new equals true. Now, again, that would only work if the field called new was a Boolean field and had the value true. Okay. Now, the good thing about that is because it's an equality comparison, it is indexable. Okay, so JSON path is indexable if you use equality constraints. Now that might change in the future, but right now the exists is not indexable, and the equality is indexable. Now note here that we're doing a search, an equality search using the double equals operator, okay, which might be familiar to some developers but not others. But the important thing to note is that it's a double equals, not a single equals. So that allows us to search for a field with a particular value, but we can also look through particular arrays. For example, if we want to look into a field called tags and actually look at the values within that, if I reference back to my example, you'll see that the field tags contains 3 values in an array called blue, green, and red. Okay, so actually, when we reference the tags field, we actually could be talking about any aspect of that. So that's why in square brackets after the tags keyword, we put a star, meaning look at all of the values in that array. And what we're then saying is, does any of the tags in that field equate to the value A? So again, if I reference my example, you'll see, because we've got values blue, green, and red, if I look for the value A in there, it won't find it. Okay, whereas if I'd have looked for the value green, it would have returned true to that query. So what that means is we can then do, if we look at the third query on this slide, we can actually look for one tag in an array of tags within a JSON document. So this would only apply to a field name called tags that is one down from the root of the JSON. So the dollar represents the root, .tags represents a field that is one down from that root, and then the bracket star bracket references all of the values in that particular array. And now that is also indexable. Now we could also look for values using something like a between clause. And what we can use here is to say $.price. So we're looking at a field called price that's one down from the root. So it's in the essentially in the top level field name. And then we're going to filter, which is the question mark, and then bracket at greater than 11.0.8, and then another filter that says that we're also less than 11.12, and that's the equivalent of a between, because we're searching for values of price between 11.08 and 11.12. Okay, now as you might expect, that's a little bit more complex than we've seen, and that type of query is not indexable. Okay, so the question mark adds a filter into the expression, and we can actually concatenate many different filters to build up a complex search. So these are some basic ones, and you can already see that this is quite difficult to understand. And that's where we can introduce much more complex queries into this. So we can actually use logical connectives, logic meaning logical and, logical or. So you can see in the second example query, I'm actually using a double ampersand there to represent and that's then also exactly the same query as we'd just written before. So instead of appending multiple filters together, we're actually using one filter with logical connectives, and I think that's slightly easier to read in the second form. And the next query is also identical to the first, but it's written in a slightly different way. So instead of referring only to $.price, we are putting a filter that allows us to refer to different field names in the current value. So we say $bracket at $.price, and then we could, if we wanted, instead of referring only to price, we could actually refer to multiple column names in that particular filter. So there are many ways of writing the same query here, and it does take a little while to find out exactly the type of query that will be useful. Personally, I found this quite fiddly, and I think it really does emphasize the need for automated testing in your applications, because obviously it makes sense to run a test query to check that it's actually working before you use it in your production SQL. So the @ sign here denotes the current location in the search, and the dollar represents the top or the root of the JSON document. There's also some additional search types that you can use. For example, the starts with predicates allows you to search for fields that begin with particular search strings. So this is a very complex search language, but it's also deliberately designed with JSON documents in mind. Now, as I've already referenced a couple of times, the JSON documents are or can be arranged actually in a tree-like structure where some fields contain sub-JSON and then even JSON within JSON. Okay, and that allows you to have extremely complex JSON data. And the JSON path queries do actually allow you to search very cleverly within these trees. So the first thing that you need to do is make sure that you're using the question mark operator, because that's the one that's that works best for filtering. So what you do is you traverse to a common starting point in the tree and then filter by specifying different arms of the tree based on the current location. So if you look at the way that the example JSON is structured above, you'll see that there's a field called My App, and within My App there's a field called Cust and a field called Tags, and then Cust also has JSON within it with a field called Address, which has another field called Country. Okay, so quite a complex tree of JSON. So what we can do when we search that is we can go to the top level of the document, which is the $, and then we say .myapp allows us to descend one level to the My App field, and then we say .cust allows us to descend a further level to the field name Cust, but only a field called Cust within the My App field. Okay, so another field that was also called Cust, but in a different location in the document, would not match. Okay, and then once we're at that location, the ampersand is the current location that we're going to use for the other parts of the search. So once we're at that location, we put in a filter, which is a question mark, and then bracket ampersand .addr.country. So that's the field within Cust that's 2 down, and we're looking for a value of UK with an equality search. And then as another filter, we're also looking from the current location for a field called tags that contains any element, the value B. So this search will return true, and therefore it will return the whole document. So the way that works is the select clause evaluates the where clause on each row in the table J, and it will return the whole value of JDoc if JDoc contains this search clause, or if it returns true from that search clause. Now, an important aspect of this is if you make a mistake and you look for a field that is not there, okay, then it won't throw an error, okay? Now, that's considered a good thing because obviously, if you say, does my JSON consist of a field called surname, and there isn't a field called surname, you don't want to throw an error just because you did a search. You want to get, no, there isn't any rows. Okay, so if you look for a missing field, nothing happens. Okay, now that's an important point because it's useful, but it's also possible to make a mistake in the way that you do queries and always end up returning 0 rows. So one of the things that we're going to look at later is how do you actually know what your JSON contains, and how do you make sure that you're writing sensible queries within JSON? Well, it's a difficult point, but it's up to the application developer to make sure that they're doing that correctly. Now, if we're using equality searches, and even if we're doing equality searches on multiple branches of the tree in the way that I've done here, the query is still indexable. And obviously, you test indexability using an explain. So the next thing that I'm going to look at is actually how to design schemas using JSON. Now I've got a kind of couple of random points here about JSON to make before we get into the details of how to check things. So when I looked at Mongo, I saw that quite a few JSON fields contained this thing called _ID, and I thought, well, how would I do that if I wanted to add an _ID field to a PostgreSQL JSON document? How would I do that? And so what I've done here is I've set up a sequence, and then I've set up a function called _ID auto that is going to be used within a trigger. And what is going to happen then is I can actually add that onto every single JSON document in my table using that trigger. So whenever I do an insert or an update on that table, it will automatically execute this function, and it will append the ID field onto the front of the document. Now there's some interesting formatting there going on, but the idea there is that it's going to automatically add that to each field. And once I've then done that, because the sequence is generating unique values, I can actually create a unique index on that, which will allow me to query directly against that field. Okay, so as we've seen, other databases also use the _ID field, and PostgreSQL can use that as well if you want it to. Okay, so there's no need to do equality searches on other things. You can actually add a unique field if needed. Now, what I was saying before was that if you wanted to put searches into your database, into your JSON, then you would want to ensure that the contents of your database actually contains the correct formatted JSON or correctly valid JSON. So what I'm showing an example here is how I can use that search criteria to actually create what's called a check constraint. And what that does is it actually checks that any incoming data that I try to insert into my table will pass this query with a value of true. If they don't, they will be rejected. Okay, and as a result, we're actually able to validate the JSON that we're putting into the database at the point of insert. The purpose of this is to ensure the data quality of the JSON data within Postgres. So this is showing how the Postgres check constraint can be used along with the JSON path query to build up a structure definition of things to check within the JSON document. And just as an example, I've inserted some data into there, and yes, that's valid and it works. Obviously, it will throw an error if the check constraint did not come back with anything. Now, what this allows you to do is it allows you to implement any level of strictness that you want within your JSON documents. You don't need to specify a JSON schema. You don't need to test everything in your JSON. You just need to check the important parts of the JSON to see if it's there. And you can see the quite nice layout there with the exists command allows you to see how you can build up a whole set of tests to apply to your JSON document. Now, I said before that the exists search is not indexable, but it doesn't matter because when we're doing inserts and updates, there is only one row being inserted at any one time. So we're not searching the table, we're searching the incoming row. So when I say the word indexable, what I mean is if you create an index on the JSON, as I showed in the last part of this webinar, so in part 1, in order for the index to be used, you need a search term that is indexable and an index. And if you don't have both of those things together, then the index won't be used and your query will not be optimized. So there are some types of question that are not indexable, and there are some types of question that that are indexable. So I mean, that's just the way life is. Not all questions are able to be answered sensibly with an index. Okay, so if I say, select count star from people in the UK, then quite clearly that's not something that would be easy to index because you have to look at all the records, right? So by indexable, we're saying, does it bring back a sensible number of rows? Now, even if you use an indexable term, it's also possible that the statistics might not reflect that, and you might not be able to use that query. So this is all down to the way that the cost-based optimizer works within Postgres. So I won't say any more about that. Now, the JSONB syntax, does that get back ported to JSON? No, basically JSONB and JSON are two different data types within Postgres, and a lot of the functionality that I'm showing you does only work on JSONB data types. Okay, but I mean, that's not particularly difficult. All you need to do is use the keyword JSONB within your tables rather than the old format of JSON. Okay, how do I get rid of that? Like this. Cool. Okay, so the next thing to talk about is how Toast works with JSONB. Now, JSONB is what we call a toastable data type. and that TOAST stands for the oversize attribute storage technique, or how do we handle long column values. So what happens with a long column value is that if the field is longer than 2K by default, then we take the value out of that column and we put it into a side table called a TOAST table. Okay, and that way you end up with actually two tables, your main table and another hidden table called a TOAST table. You don't notice it's there unless you're a DBA and you look inside as to how things are stored. Okay, now the reason that we do that is obviously there's a limit to how much data that we can fit on any one data block. But we also want Postgres to be able to support very long records and handle any size of JSON. So if the JSON's really big, then what we do is we chop it up into pieces and store that as multiple rows within the TOAST table. So you can store JSON data up to 1 GB in size, and that will end up as lots of individual chunks within the TOAST table. Now, shorter values will be held in the main table. So if you've got data that's somewhere above 2K or is sometimes above 2K, you might want to play with a parameter called TOAST tuple target, which I added to Postgres in order to allow people to change the way that gets stored. This allows you to store medium length JSON within the actual table rather than getting sent to the TOAST table. Okay, because once it's in the TOAST table, it takes a little bit more effort in order to get that data back from the TOAST table. So that's something that you might want to play with if you've got medium length JSON. If you've got short JSON, it doesn't matter. And if you've got long JSON values, it also doesn't matter because it's definitely going to end up in the TOAST table. So why does this matter? Well, because of physical effects. If the data for your JSON is not updated when you do an update statement, maybe you're updating some of the other columns in the table, then the toasted data will not be affected. Okay, so it's actually more efficient to store things in that way. But if you change any part of the JSON data, then that will cause what's called a non-hot update, and it will potentially bloat the table, and that's why we need to run vacuum in order to recover from that. So one of the things that I suggest is that if you've got parts of the JSON data that are being frequently updated, that you actually pull that field out of the JSON and put it separately as a column within the same table. Now that will then allow that column to be updated without changing the rest of the JSON. And if the JSON is in the TOAST table, then we just leave it there and we'll actually only do the updates on the main table. Okay, so this is basically a good idea to separate your very hot data items from the rest of the JSON if that's possible. Now, obviously, this is not something that happens automatically. It's something that you would need to do as a database design technique. Now, another thing to consider when we're using JSON is that it can be quite large, and so we need to think about how compression would work. Well, the default settings for JSON are okay. What will happen is when it's moved into the TOAST table, it will be automatically compressed, which is useful to a certain extent, but the compression is not as good as it might be. And so what we want to have a look at is some other mechanisms for how compression would work. Very specifically, the TOAST compression isn't effective with field names, because the field names tend to be unique within the JSON blob, and therefore, because they don't repeat, there's nothing to compress. Okay, it doesn't matter that the fields all contain that field name, they still won't be compressed. So what is the effect of that? Well, what that means is that if we've got a JSON blob that looks like this, very simple, it is one field saying very long field name and then a value. Now, what we do is we store all of the field name. So because very long field name is 18 characters long, that means we store that value as 18 bytes of text within each JSON column. And that typically won't be compressible. So what that means is every time you use the very long field name that I've got there, it will be an 18 byte overhead per row within the database. And obviously, if you've got quite long JSON, all of which has got very long field names, then you end up with quite a substantial overhead for the JSON data. So can we do better? Well, yes, we can. There's another data type, which is open source, produced by Postgres Pro, but EDB also has an enhanced version of Json. Now in Json, we actually compress the JSON by using a compression dictionary, and this dictionary allows you to map the field names through to just a binary field name. And what that does is it gives you typically 2 bytes per field overhead rather than, as you saw, 18 bytes. So 18 bytes down to 2 bytes means that in practice, Json can be particularly effective at compressing JSON data. So it's a good thing to use. But what I would like to point out is that if you store JSON data, instead of as in JSON, if you store it in fields, or sorry, if you store it as columns within a Postgres table, then there is 0 overhead per row, because the field name or the column name is actually stored as metadata within the Postgres catalog. And so there's 0 bytes per row overhead. So the actual very best way to store data in Postgres is actually as columns, okay? And that is why we encourage the use of separating data into columns. Now, that is a big statement. I understand that, and I'm going to explain it because you know, I wouldn't want you to think that there's anything wrong at all with JSON. That's why I'm doing the webinar, right? So I've got quite a long explanation of how this is going to work. So please bear with me. So one of the things that you might want to do is actually analyze the contents of your database to see what fields that you've got within that. And what we can actually do is use a query like this, select JSONB object keys as key, comma count star from J, group by key, order by count star. What that will do is the JSONB object keys pulls apart the JSON into a set of fields, and then it passes it through this aggregation query. And what that will do is it will produce a table which is one row is each unique field name within the table, and the frequency of on how many rows that field name exists. And you can see that I've done that on a table that contained 100,000 records, and I used my example test data. So obviously your data is going to look quite completely different. But what this query allows you to do is a frequency analysis of the JSON fields to see which fields are present all of the time and which fields are present just some of the time. So obviously the price column there is present on every single row in the table, whereas the field called new is only present in 25 out of 100,000 records. So bringing that out into its own column is not actually going to be particularly useful for compression, okay? Whereas bringing out the price and the OTS fields from the JSON would be particularly effective in compressing. So in general, my recommendation is that you use JSONB all of the time, okay? And there's very few reasons why you would want to use JSON at all, okay? It was an earlier attempt within Postgres to support JSON data, but the JSONB data type is a much better way of representing the data. So what I'm now going to do is I'm going to explain some of the ways that you would like to use JSON within your applications. And that's quite important, because all this talking about, you know, bringing fields out of JSON and having columns, when would you be able to actually do that in practice? And actually, it turns out that there is some ways that you might want to think about doing that. Now, obviously, the simplest type of application is where we take JSON from the application and we just put it straight into a JSON data type within Postgres. So that's what I mean by direct storage. We just take the JSON and we store it in the same format in which it was sent. But there's another way of looking at that, and that's using this concept of a data mapper, which is a design pattern that says that it's okay to change the format of the data. So what we might have is we have JSON externally, for example, a messaging service that's sending us JSON data, but we want to store that in columns in the database. It's perfectly fine. We just have to map from one to the other when we store things in the database. Or we could actually do this the other way around. We could have tabular data or columnar data coming into the database, and we choose to store that as JSON within the database. Okay, and so what we're seeing is that actually what we store and what we give out to other people can be completely different things. So using that design pattern, we can actually rethink the way that we're storing things within our database. So there's quite a few other use cases for JSON. Tagging, for example, which is quite useful when we've got very heavily normalized schemas in sort of fourth or fifth normal form. They can be denormalized a little bit by using tagging. Tagging is also particularly important for AI applications, where we want to actually record certain events for certain records, and it allows us to train models using the tags. So particularly interesting to have tagged data. So that's in my mind quite a key use of why we would want to use JSON. There's another way that you can use JSON, which is called a single view. The idea here is that you bring together all of the contents of multiple different databases into a single database cache that can be actually a lot more easy to use, and that's particularly useful when you're trying to get, say, a single customer view. So this is actually an enterprise architecture design pattern that we can actually implement easily using JSON. And of course, other use cases might be to migrate away from JSON only databases, for example, Mongo or other ones as you choose. So there's actually a lot of reasons to use JSON, and there's also a lot of ways that we can use JSON. So what I'd like to do is explain this data mapper design pattern to you a little bit more. The idea is that we're taking, we're going to map from a JSON, a piece of JSON data. We're going to map that to a view. So we're going to start with data in a table, and we're going to output that as a view. We could also do it the other way around, but I'm just going to show you this one example. So what we do is we take the sample data that I had before, which had the OID field, the OTS field, the tags field, etc. Within it. What we're going to do is we're going to create a tabular representation of that data structure. So we're going to simply create a table with lots of Postgres data types in it that map one-to-one to the fields that existed within the JSON. And then I'm going to use the create view syntax here to create, which is what that's going to do is it's going to map between the JSON and this definition of table. Now it's a very simple query that I've used there, but it's actually extremely powerful. And it uses a function called JSONB populate record. And what that does is it literally takes the JSON, it reformats it into a Postgres record and allows it to be viewed normally. So if I show you the output from that view, you'll see that it's taken the JSON data and it's now representing that same data as columns in a table. Okay. Now, obviously it's a view that I've used here, but I could have mapped that directly into, I could have stored it as a table if I wanted to. That's just up to you whether you use a view or a table. So that's taken the JSON data and now shows it as tabular data. But I've lost some data there because there was an ADDR field in the JSON that hasn't yet appeared in the output. And that's because in this table here, I chose not to include the ADDR type. And the way that the JSONB populate record function works is that it will only work for matching field names, okay, and it discards the remaining data, which doesn't sound that useful. So what is useful about JSONB populate record is that it's got quite a heavy set of conversion rules. Now these are great. I'm showing you this because I want you to know how complex it is. Complex in this case, meaning extremely clever. It does a very clever conversion between the JSON and tabular column style data. Okay. So I'm not going to read out all of that because it would be ridiculous. But what I wanted you to do is give you the flavor that it's quite a complex conversion embedded in just a simple function. Okay, so a lot of people might have a JSON to column conversion tool. Well, this is the Postgres conversion tool, just encapsulated in a single function. Now I can actually change that to pick up the missing data simply by changing the definition of the view slightly. And what I'm able to do there is actually pick up this ADDR field that I had in the JSON, and that will actually add that data to the output of that query. So what I'm saying here is that this allows you a very complex or feature-rich way of mapping from JSON data to columnar data. And that's particularly important because that allows us then to send and receive data within your applications and yet store the data on the database using Postgres features, splitting the fields up into columns as needed. And what that allows us to take advantage of is what I've called implicit compression. Now, implicit compression is not a term in the documentation, okay, so don't look that up. What I mean by implicit compression is what I said before, which is if a field name was stored directly in the JSON, then that field name represents an overhead per row if you remember that I had a field name called very long field name, which was 18 characters long, I'm saying that each record, each JSON document would have an 18 character overhead just for that one field. And obviously, if there were 100 fields in the JSON document, there'd be a proportionally larger overhead. And what we're going to do is if we take that JSON and we move it outwards into its own column, it then doesn't have any overhead at all. So we've gone from 18-byte overhead to 0-byte overhead. Now that compression, that field name compression, is implicit, okay, because that's the way Postgres works with the definition of column metadata. And as a result of that, you get like quite an extreme benefit from separating out the data into columns. And as I pointed out before, it also allows you to utilize different update-friendly designs. So what I've shown you here is that you can, if you wish, store JSON data within Postgres. We do that extremely well. If you want to store very large volumes of data within Postgres, then what I'm saying is you can use this data mapper concept to store the data slightly differently within your Postgres databases in order to make them more compressible and smaller, which obviously has benefits for the speed of particular operations and backup and such like. Okay, so depending on how large your database is, you might or might not want to take advantage of this opportunity. So the next things I want to talk about really is to sort of clear up a few other points around JSON. What I've been showing throughout this webinar is that the types of function that we support in Postgres are quite advanced. They're very useful for doing a whole range of different things. What we have here is just simply a whole swathe of functions that are dedicated to manipulating JSON data. And as you can see, there's 65 different functions, 11 of which are operators, 14 of them are for JSON path, but the others are all utility functions that allow you to manipulate and use JSON within your applications. So a very advanced set of functionality that allows you to store and index your JSON data on Postgres extremely well. There's some other ways that you can manipulate things. There's a language called PLV8, which is a procedural language for Postgres written or that allows the user to write JavaScript queries. Now, unfortunately, there's some issues with the stability of that, and it's no longer available on some platforms, but it is something that you might want to take advantage of. Another thing that you might be interested in is that there's an open source extension maintained and supported by EDB called the Mongodb Foreign Data Wrapper, or FDW. And this allows you to query the data within Mongo directly by running a query on Postgres. And that works not just for selects, but it also allows inserts, updates, and deletes through the foreign table wrappers. So as an example of how that works, we can create a collection inside MongoDB called TestDB, and then we can insert data into that collection. Here I'm inserting 2 different JSON documents with some sample data in. And then what I'm going to do is I'm going to use that from PostgreSQL. So first of all, I create an extension called Mongo_FDW. What this does is it loads a dynamic module that has all of the code within it to access Mongo. So that's the first thing that we need to do. Then we define a server called Mongo server. Now this is my like a kind of view of the Mongo server. I'm not actually creating a new Mongo server. I'm creating an object that looks at that Mongo server. So create server Mongo server using the foreign data wrapper technology, and then with some options. And then I create a user mapping for my user. So I'm actually creating a user mapping for myself, and how the user defined within PostgreSQL maps to the user and the security options, if there are any available within Mongo. Once we've got those two things set up, then I can create something called a foreign table. Now, a foreign table is the term used by the SQL standard. It's not actually, it's not actually a table. It's more like a view, because when you say selects from this table, this query actually it gets decomposed. It gets changed into requests that would be recognized by Mongo, and then it gets sent to Mongo. The data comes back, and then we reformat it again into Postgres data format. And so what this has allowed me to do is these commands are sufficient for me to access the data that I created here. And you can see that I've executed a query that will return all of the data where warehouse is 1, and you see that only one of the rows has got warehouse ID equals 1, and as a result we expect one row to be returned for this query, and that's exactly what we get, and that's the output to the query. So very simple to use. If you can't work out what the mapping should be between the warehouse or the particular collection and the Mongo data, then you need to write that out manually. EDB does have a tool to make that easier, but this simple command, import foreign schema, doesn't yet fully work with the Mongo DB foreign data wrapper. And there's a number of other foreign data wrappers available as well that that implement similar access paths through to other data stores. So Postgres really is a very easy to use system with regards to accessing data in other databases. So that's a number of points about JSON. What I wanted to do now is talk a little bit about the SQL Standard, and what we're seeing in later releases of the SQL Standard is JSON is actually now a full-strength data type within the SQL Standard, alongside things like integers and alongside XML as well. And that's come about in the last few years, and that really has come about because of Postgres's interest in JSON data. We're the people that have really made that work within relational systems, and that showed the SQL committee what was actually possible within modern systems. So that's now making its way into the SQL Standard, and what we're seeing is that the SQL JSON definition is very similar to, but not exactly the same as, some PostgreSQL features that already existed in Postgres for many years. So the actual syntax that's been adopted is closer to the syntax from Oracle and MySQL, and so we're actually updating support for this type of syntax within the latest version of PostgreSQL, again to make sure that we are as standards compliant as possible. So if you followed me through this whole presentation, and I've freely admit it's been what I would call an advanced webinar, so it's possible that I may have lost some of you that are not following the details of JSON or Postgres, but I'm sorry for that. But there is a requirement to cover the more advanced topics rather than just the basic stuff. And in doing so, we persuade everybody that actually Postgres handles this data extremely well, which is what you really need to know before you use this. So the vision is that Postgres follows all of the available standards wherever they exist. So that's SQL, IEEE, OGC, IETF, Unicode, and many others are all standards that are followed by the Postgres database. And there are many new standard compliant features being added to Postgres 14 and many being added to Postgres 15 and beyond. And this gives us what I've previously referred to as hyper-converged Postgres, where lots of different ways of manipulating data are integrated into one robust and secure database by using various data types. So we've got relational data, we've got document style data in JSON, XML, as well as ways of analyzing that in full text semantics. We support time series data as well as temporal historical data, graph and geographical data, all within the one database. And that vision continues, that there isn't a favorite style of data within Postgres. It isn't just a relational database. It's a database where you can put the type of data that you have within it. And that's quite an important point. So Postgres obviously comes about because we are post-relational. We are not just a relational database. We cover JSON and many other data types. And what we're seeing is that EDB is contributing to Postgres. We're adding features for JSON, but there's also ways of extending Postgres being published. So I just wanted to thank a few of my colleagues for various blogs and pieces of information, and especially Andrew Dunstan for doing a lot of the core committing around JSON style features. So thank you very much, Andrew. And thank you very much to my other colleagues there. So that brings us to the end of part 2 of this webinar. You will have noticed it was an advanced webinar. If you want to find out more, if you didn't look at part 1, perhaps you should go back and have a look now. The slides and other information will be available, and I will also endeavour to look at some of your questions here now, so we can see if I can answer some of those. So no, there isn't an instruction book with Postgres. We're expecting a lot of this content to be available on enterprisedb.com. Yeah, and there'll be various types of demonstration or example available there. Yeah, so there's one thing to say when you use JSONB data is that it does actually change the order in which you it does change the order in which you have fields within the JSON document. Now, JSON is supposed to be agnostic of that order, so you shouldn't be relying on the order in the original JSON. If you really do want to preserve the order within the original JSON, then you should just simply use the JSON data type rather than JSONB, and then manipulations will need to potentially map to JSONB in order to use that. So I freely admit that it's been an extremely advanced presentation, and I understand that you may not have questions, but if you do have more questions, please ask them now. Otherwise, I'll say thank you very much for listening to me today, and look forward to seeing you on future webinars. So thank you very much, and see you again soon.
Great. Thank you, Simon. Have a great day, everyone.
Thank you.